Hello everybody, this is the third lecture of Coulombium, and I'm gonna go through KSP. I start with the KSP, and then I will move to the common ion effect, the Le Chatelier effect, and at the end, if I get time, I will try to go through delta G. Okay, so what's a KSP? KSP, when we say KSP, we are talking about the equilibrium constant for solid phase. The meaning of this is like you have equilibrium that in that equilibrium there is a solid. Okay, let's say we have AB solid under equilibrium with A plus B. Okay, this is equilibrium. Because it's equilibrium, you will say K. Okay, and then you say concentration of A plus multiply concentration of B minus under equilibrium condition. But because we have a solid and we want to say, like, oh, there is a solid in this equilibrium, so keep it in your mind, and we say SP or solid phase. Okay, so in this case we have mx2 solid under equilibrium with m2 plus 2x, so it will be m plus 2 multiply concentration of x to the second, okay, because we have 2 from x. Okay. So it's not really something different than normal K that we write it for any chemical reaction. Only difference is like we give SP as a subscript for it. So I can call this one KC because I'm using concentration for any product. Okay. Here, look at this question. It says calculate the KSP if the concentration of the concentration. Okay, so if the concentration of lead is equal to this number. So let's write the K for example first. So Kc, which is equal to KSP, is going to be equal to concentration of lead to here with plus 2 charge multiply concentration of chloride, and we have 2 of them. Okay, and I need to get the K, okay, or KSP. In order to get it, I need to know what's the equilibrium concentration for the lead and chloride. So they are saying under equilibrium condition, so if we assume there is a beaker, we have chloride and lead under equilibrium condition. So we have these 2 ions inside the solution. And they are saying lead, we have it equal to 1.62 multiplied 10 to the power of minus 2. Okay, so I'm going to say this one. Under equilibrium, concentration of chloride, based on this formula, is 2 times of lead. 2 times of concentration of lead. Because the formula, it has 2 chloride per 1 lead. So now, if you know concentration of lead, you will multiply it by 2 and you will get the chloride. So it will be 2 multiply lead, it says 1.62 multiply 10 to the power of minus 2 molar. So concentration of chloride under equilibrium condition is going to be 2 times of this number. Let me silent this one. Okay. So it will be 2 multiply 1.62 minus 2, and that's going to be 3.24 multiply 10 to the power of minus 2 molar. So KSP, it will be concentration of lead, which is 1.62 multiply 10 to the power of minus 2 multiply concentration of chloride, which we just got it, so multiply 1.62 to the power of minus 2. That's going to give us 5.0 5.25. So I get 5.25 multiplied 10 to the power of minus 4. Okay. Okay. Let me just double check one thing. I want to be sure that I got this calculation correct. So we have 1.62 to the power of minus 2 multiply 3.24 to the power of minus 2, and that's going to be I forgot something. Sorry about it, guys. Sorry about it. I forgot that we have 2 there. Okay, we have 2 there, and because the chloride is it says chloride to the second, so I did not apply this one, so sorry about this. This is not going to be correct. Okay, so it's going to be this number to the second multiply 1.62, and that's going to be 1.70 multiply. Okay, so forgive me about this one. KSP, it will be 1.70 multiply 10 to the power of minus 5. Okay, and that's the correct answer for it. Okay. Another example from KSP. They can ask you about something that we call it molar solubility. What's a molar solubility? Molar solubility is, you want to figure that how many mole from the reactant, okay? How many mole from the reactant dissolve in 1 liter? Okay, so how many mole, number of moles per volume in liter. Okay, now look to this one. It says 1 mole of silver sulfate. So the coefficient is 1. And it will give you 2 mole of silver. If you know how many silver you have, you divide it by 2 to get number of mole from silver sulfate. Okay, or simply focus on the sulfate. The coefficient is 1. If you know how many sulfate you have, because the coefficient is 1 to 1, that means you figure how many mole of silver sulfate you dissolve. So I'm going to define the KSP, and it's going to be equal to silver to the second multiply sulfate. Okay. Now, I'm going to say here Ag2SO4 solid under equilibrium with 2 mole of Ag plus and 1 sulfate. Okay. Now, let's write the initial concentration. What's the initial concentration for silver sulfate? Hey, this one is solid. So we don't care about it because it's solid. It's not going to have any concentration. Okay, we don't care about it. How about this? Okay. How about this one? At the beginning is going to be 0. Okay. So I don't have this one right now. Because I don't have it, that means I do not have any equilibrium. So in order to have equilibrium, we need to generate ions. So I'm going to say minus X minus something. Okay, how much from silver I'm going to get? I'm going to get 2 times of whatever I'm losing. And here, I'm going to generate 1 time of X. So under equilibrium condition, I will have here minus X from this solid. So minus X, which we don't care about it, because again, this is solid, we don't care about it. How about this? 0 plus 2X, it will be 2X. Sulfate is X. Okay. So now, you know the concentration for silver and concentration of sulfate. Put them inside the KSP formula. So you will have 2X to the second, and sulfate is going to be X. So we go, again, KSP. So I'm following this formula. Let's call it 1. I'm following 1. And KSP, it will be equal to silver, it will be 2x. So you go 2x to the second, have a sulfate x. So we get 4x squared multiply x, and that's gonna give us 4x cubic. Okay. Now the question gave you the KSP. So the left side you have it. You have it 1.4 multiplied 10 to the power of minus 5. And this is equal to 4x cubic. So cubic x is going to be equal to KSP divided by 4. So x is going to be the third root of this number. And x is equal to 1.5 multiplied 10 to the power of minus 2. Remember, x based on the ice table, x is equal to concentration of the sulfate. So x is equal to concentration of sulfate, and the equilibrium condition is 1.5 multiplied 10 to the power of minus 2 molar. And the silver is 2x. Okay, so concentration of silver is equal to 2x, so you go 2 multiply this number, and it's going to give you this. Okay, so now it says silver sulfate, if you dissolve it 1 mole, you get 2 mole silver plus 1 mole sulfate. The molar solubility for Ag2SO4, okay, it will be equal to concentration of the particle that has coefficient of 1. So it will be equal to concentration of sulfate under equilibrium condition, which is equal 1.5 multiplied 10 to the power of minus 2 molar, or x. Okay. Try to practice this one for yourself. So there is aluminum sulfide solid under equilibrium condition with 2 aluminum plus PS minus 2. And KSP for this one is given. I will give you the KSP, and the KSP here is equal to 8.7 multiplied 10 to the power of minus 34. Okay, KSP is there. So you go with initial concentration. We don't care here, solid. This one 0, that one is 0. Change, we're gonna lose something from the solid. We're gonna generate here plus 2x, and this one it will be plus 3x. So under equilibrium condition, we're gonna get minus x, which we don't care because it's solid. How about this? It will be 2x, and that one is gonna be 3x. So KSP, it will be aluminum, the second multiply sulfide to the third. So you go 2x to the second multiply 3x to the third. Okay, so you have KSP, which is equal to 8.7 multiply 10 to the power of minus 34 equal to 4x squared multiply 27 cubic x. Okay, so we go 4 multiply 27, and that's going to be 108 x 5. So x is going to be the fifth root of KSP, 8.7 multiply 10 to the power of minus 34 divided by 108. Divided by 108. Okay, 8.7 minus 34 divided by 108. Power of 1 divided by 5. That's going to be 9.58 or 9.6. 9.6 multiplied 10 to the power of minus 8 molar. What's the x? We don't have any compound that has x. Okay. So we need to, we need to find concentration of those and define the molar solubility. Okay. This is says if we go with 1 mole, we get 2 mole aluminum and 3 moles of sulfide. So if you want to know what's a molar solubility, you want it to be just 1x, and that's gonna be here. That's gonna be the correct answer. So molar solubility is gonna be 9.6 multiplied 10 to the power of minus 8. So molar solubility is gonna be equal to x, and is equal to 9.6 multiplied 10 to the power of minus 8 molar. Concentration of aluminum is equal to 2x, and concentration of sulfide is equal to 3x. Multiply 9.6 multiply 10 to the power of minus 8. Multiply 2, that's going to give us 4.8 multiply 10 to the power of minus 8 divided by 2 multiplied by 3, that's going to be 7.2 multiplied 10 to the power of minus 8 molar. Okay, so I got you the molar solubility, and also I got you the equilibrium concentration of aluminum and sulfide. So I think we practiced enough. Question from a KSP. Let's move to new subject, and that's gonna be the Le Chatelier effect. So the Le Chatelier effect, it says if you have an equilibrium, that equilibrium will try to keep the equilibrium condition to some extent. So meaning of that, it will resist against, change with the equilibrium condition. Okay. It will try to move in a direction to keep the equilibrium condition. Okay, to keep the equilibrium condition. And if you keep, giving it too much stress, when I say stress, you increase the concentration of one reactant dramatically so that you lose, the second one. Then in that case, you're not going to have equilibrium, or you play with the temperature or pressure, volume, and you increase or drop them so down. So then you will actually stress the equilibrium in a bad way, and you will lose the equilibrium condition. So in this case, we have A molar from A plus B molar from B under equilibrium with C from C, and plus D molar from D. And it says if you increase concentration of product here, those are product. if you increase concentration of them, because you want to keep the K constant, K is constant, and K is equal to concentration of product over reactant. Okay, so if this one goes up, K is not going to be constant. We need to manipulate it. And so if you increase concentration of reaction, it will move back. So the reaction, it will move to left to generate more reactant. Okay. So it's reaction, it will move to the left. Okay. If you decrease concentration of product, so if concentration of product goes down, this time, if this one goes down and you divide it by R, concentration of reactant, K will be a small number. So K is not going to be a constant number. So we need to, regenerate product. We need to increase the concentration of product, so then it will be like an equilibrium condition. So the reaction, it will move to the right side. Okay. Increasing concentration of reactant. If this one goes up, that means your denominator is going up. Numerator divide by denominator, and denominator is bigger now, so K it will be small. How can I keep K, constant? Drop concentration of the reactant. The reaction, it will move to the right side. So more product, or I should say generates more product. Again, more product. And if you decrease concentration of reactant, okay, if this one is going down, we need to force the reaction to move back and generate enough from reactant. So the reaction, it will move the left side to more reactant. Okay, that's the Le Chatelier effect. Okay. Now, what will happen if we change temperature, volume, or pressure? Okay. Now, first thing that you need to ask yourself, whether that reaction is it's exothermic or endothermic. You need to determine that one, okay, because the story is going to be different. Okay, so if we have a reaction that is endothermic, okay, reaction like this one, endothermic, and if you increase the temperature, okay, because this is endothermic, so you need to give it heat to apply to move the reaction to the right side, okay, because it's endothermic. This is positive. Delta H is positive. So if you increase the temperature, because you are adding heat, reaction, it will move to the right side. Okay, so the reaction, it will move to the right side. That means you will have more product, less reactant. Okay, so what will happen in this case? If it's endothermic and you give it more heat, you will get more product, less reactant. So K, it will be a bigger one. K, and increases. Okay, K and increases. If you drop the temperature, K decreases. Okay, K is subject to temperature. K is constant until temperature is constant. If you change the temperature, K is not going to be constant. And K, it will follow the fact that your reaction is endo or exothermic. Okay. Let's, focus on this, slide and come with more examples. Okay. We have NO, 2 mole of NO plus Cl2 delta H of this reaction is negative and is equal to minus 97.2 kilojoule per mole. Okay, so this is exothermic reaction. Okay, let's define the K. K is going to be equal to product over reactant. You have NaCl to the second divided by Na multiply Cl. Okay, equilibrium condition here, equilibrium. Okay, first one. What if I say increase temperature? So T goes up. What will happen? Okay, now because this one is exothermic, it will generate heat for you. So you say 2 mole of NaCl plus heat. Heat is on the right side. Okay, heat is on the right side. So if you increase the temperature, heat or the product is going up. Okay, heat or the product side is going up. So hold the reaction, it will move back to the left. Okay, reaction, it will move left to generate more reactant. So now define K. K product over reactant. Concentration of reactant went up. Concentration of product went down. So what will happen with the K? K, it will go up. If T goes down, reaction, it will move to the right side. If you use heat, or if you put this reaction in an ice bath, the second you generate heat, it will be taken by the ice bath. So we don't have heat. Because we don't have heat, we need to generate more heat. So this one goes to the right side. That means K, it will be equal to product, it will go up. Reactant, we are using more from reactant, so it will go down. How about K? K, it will go up. Sorry, the K, it will... My bad, that was my bad. This one was supposed to be down, my bad. Okay, that one down and this one is up. Okay, first one down and the second one up. I think I need to drink coffee. Okay. Okay, add my doping. Okay, sorry again. So the first one, because the denominator is going up, reactant going up, product is going down, then K, it will be a smaller number. How about this? We are generating more from product. We are using the reactant. So the K, it will go up. Okay, K, it will go up. So you see, an exothermic reaction, if you chill it or you cool it, you will get actually more from product. So you don't need to heat the reaction to get more from the product. It's just cool it. Okay, how about effect of, you know, pressure or volume? Okay. Okay, I go with here. When you want to consider P or V, you have to look to number of mole. Okay, number of mole. Let's go with the volume first. Volume directly connected to number of mole. Okay, if volume goes up here, or number of mole goes up, we said volume versus number of mole. If you increase the volume, you can accommodate more number of mole. So this one is N1 and that is N2. Okay. If you increase the volume, V1 and that is V2, you can accommodate more, you know, from those number of moles. So what does it mean? That means the reaction, it will move, or the equilibrium, it will move to one side that it has more number of moles. So look to this one. We have 2 mole on the product side, and reactant side we have 2 plus 1, 3 moles. If you increase volume, because you have more space, you can accommodate more number of moles. So the reaction, it will move to the left to generate more moles. Okay, so the reaction, it will go to the left side. Okay, how about K? K is constant because we did not change the temperature. Okay, if you don't change the temperature in this process, K, it will be constant. Okay, how about the pressure? Pressure inversely connected to the volume. If the pressure goes up, then volume, it will be smaller. Okay, if pressure goes up, volume, it will be smaller. Okay, here V1, so this one is P1, that's going to be V1, and if you increase the pressure, V, it will be smaller. You have a smaller volume. Okay, because you have a smaller volume, you cannot accommodate huge number of moles. So the reaction, it will move to one side that it has less mole. Okay, less moles. 2 plus 1, 3 on the reactant and 2 on the product side. So it will move to product side. Okay, how about K? K again is constant. Okay, K is constant. Okay, because I did not change the temperature. I spoke about the T. Okay, this is exothermic reaction, so you are generating heat, and if you increase the temperature, that means heat is going up. If heat is going up, you can treat this one as a product. Reaction, it will move to the left side. Okay, T goes up, reaction, it will move to the left. Because we change temperature, K, it will be affected. K is subject to the temperature. Okay, K is subject to that. This is exothermic. If we move the reaction to the left, we have more reactant, so K will be smaller. Okay. How about adding one reactant or a product? Cl2 is a reactant. If you add a reactant, reaction, it will go to the right side. So it goes to the right. How about K? K, stay constant, because we did not change the temperature. Okay. Test yourself with this. Okay. I'm gonna give you 1 minute to think about the Okay, so 1 minute, 1 minute is done. So 1 minute, you paused on it. Otherwise, it was just less than 10 seconds. Okay, this is endothermic. Endothermic process. Okay, in order to do it, we need to give heat to the reactant. So heat is here. We are adding heat to the reactant. If you add heat, reaction, it goes to the right side. So we'll have more product, less reactant. That means K will be bigger. Okay, so K, it will be bigger. K is product over reactant. So K goes up. Increasing pressure. This is liquid, that one is gas, and gas. 1 mole gas, 1 mole gas. When you're talking about pressure, you're talking about gas compounds. If you increase the pressure, volume, it will be smaller. Because volume goes down, you cannot accommodate more number of moles. So you go to one side that it has less mole. This one, it has 2 mole gases, and that one is liquid. Liquid requires less volume than gas. So the entire reaction moves to the left side, and K stay constant. So K constant. Increasing volume, and volume goes up, then you can accommodate higher number of mole. One here, this one is liquid, we don't care about it. One gas, so the reaction, it will go to the right side. Okay, K, again, constant. Decreasing concentration of sulfuric acid. If this one goes down, you need to regenerate it. Then you can keep the K constant. Otherwise, K is not going to be constant, and you did not change the temperature. So K, it will be constant because you did not change the temperature. So how can I keep K constant? I will regenerate some from sulfuric acid. So let's say you added something to this, equilibrium, and that compound reacts with sulfuric acid. So sulfuric acid is going down. Something is eating or decreasing, sulfuric acid. So the reaction, it will move to the left side. But K is constant. Okay, so now that we know the Le Chatelier effect and KSP, I'm going to open a new subject, and that's going to be the common ion effect. What's the common ion effect? Common ion effect is following the Le Chatelier effect. Okay, Le Chatelier principle. We're saying that, like, we have an equilibrium, like lead iodide is under equilibrium with lead plus 2 from iodide. Okay, if you add iodide, lead or iodide to this system, it will move to the left side. Or if you react this system with something that is using iodide or using lead, reaction, it will move to the right side. Okay, so common ion effect. What's a common ion? Common ion is ion that you are adding and is equal to either lead or iodide in this case. So for example, if you are adding sodium iodide, the common ion, you look to here, 1 lead. I don't have lead inside the formula. I have iodide, so this one, it will be the common ion, the one that they are sharing. If you add lead nitrate, the common ion in this case, it will be the lead. Okay, so you will have 2 sources that they are generating iodide. One is the lead iodide, and the second is sodium iodide. Or if you are adding this compound, in that case, you have to tell yourself that lead comes from 2 places. One from the lead iodide, and one from lead nitrate. So I need to include that one in my calculation. Okay. And what's the effect of adding any of this as a common ion? If concentration of iodide or lead goes up, entire reaction, it will move to the left. Entire reaction, it will move to the left. So what will happen? Molar solubility of the reactant goes down. Okay, molar solubility goes down. That means you will combine 2 of cations and anions to generate a solid. Okay, look to this equation. It says, what's a molar concentration of lead if the concentration of sodium iodide is 0.1? Okay, 0.1. So you have to tell yourself that I have a solution. Okay, I have a solution that's a mix of two compounds. One is sodium iodide, and the second is lead. So it's going to be lead iodide. Okay, and lead iodide is under equilibrium. Okay, so sodium iodide is 100% soluble. It will generate sodium and iodide. Okay, so initial concentration for sodium iodide, you go with 0.10 molar. This one is 0, that one is 0. Change, it will be 100% conversion. How do I know? Because I don't have the KSP or K for it. So minus 0.10 plus 0.10 plus 0.10. So at the end, I will have nothing from lead iodide. From sodium, I will have 0.10, and from iodide, I will have 0.10. This one, it will be the common ion. Okay, that one is going to be the common ion. Why iodide is the common ion? Because look to the lead iodide. It has iodide in it. So whenever this one generate iodide, you will have effect of iodide that comes from sodium iodide. Okay, so now I know the initial concentration for iodide and sodium. Let's write the equilibrium reaction for lead iodide this time. We go lead iodide under equilibrium with lead plus iodide. Build the ice table for it. You say initial concentration, this is solid, I don't care about it, that one is 0, but check this. Please be careful about this one. For iodide, you're not going to say 0, okay, because sodium iodide generated iodide for you, and initial concentration is going to be 0.10. Before we get anything from lead iodide inside the solution, sodium iodide generated 0.10 from iodide. Now, we might get something from lead iodide, minus X, this one plus X, and that one is going to be plus 2X. So after equilibrium condition, I will have X, this one is minus X, and we don't care about it because it's solid. That one will be X, and here is 0.10 plus 2X. So now write the KSP. KSP is equal to concentration of lead multiply concentration of iodide. So you get KSP, which is equal to 7.9 multiply 10 to the power of minus 2 equal to X, and here 0.10 plus 2X to the second. 2X to the second. Now, I'm going to do one, okay. I can, do one assumption and then go forward, okay. Or do it through a quadratic equation, or in this case, it will be actually a cubic equation. And you have your calculator and get the answer for cubic equation. Okay, so I'm going to assume, 0.10 plus 2x is almost 0.10. Okay, almost 0.10. Okay, if that's the case, I go 7.9 multiply 10 to the power of minus 2 equal to X multiply 0.10 to the second. So X is gonna be 7.9 multiply 10 to the power of minus 2 divided by 0.10 to the second. And that's gonna be 7.9. Oops. Okay. So x is equal to 7.9, okay, molar. Okay, hold on. I think I feel I made. Oh, that one is 9, not 7. That is 9. Okay, this is 9. Yeah, because like I said, it can be such. It can be this big number. This is 9. Okay. This is a huge concentration, so that's the reason I was suspicious to it. Okay. It's 9, so it's going to be 7.9 multiplied 10 to the power of minus 7. Okay, minus 7. Okay. So that's the x. Okay. You want to do a test. Okay, you did assumption. You said 0.10 plus 2x. So why don't you go divide the 2x by 0.1 multiplied by 100 and see what's the answer for it. 2 multiplies 7.9 multiplied 10 to the power of minus 7 divided by 0.10 multiply 100. So I go minus 7.9 multiply 2 divided by 1. That's going to be 1 point, and multiply 100 is going to be 1.58 multiply 10 to the power of minus 3%. So it's less than 5%. So the assumption was correct. It was correct to say this is almost equal to 0.1, and we ignored the 2x. Okay, so now before I move to new, like a new question, I need to tell you when you should do, when you should, go with the assumption and ignore x. Okay. Let's say you have a reaction that says Hx, okay, their equilibrium, and you go H plus and then X minus, and K for this reaction is given, okay, and the K is equal to 7 multiplied 10 to the power of minus 6, and the initial concentration is 0.2. Okay, so initial concentration is 0.2. Okay, so we're going to say initial concentration here 0, 0. That one change, minus x plus x. That one plus x. Equilibrium, it will be 0.2 minus x. That one, it will be x, and that one x. So k, it will be x multiply x divided by 0.2 minus x. Now the question is, can I ignore this x? Okay, can I ignore it? Yes or not? You go with this one. Take concentration of Hx, initial concentration, which is equal to 0.2 divided by K. So I'm going to divide it by K. And I will multiply, divide this one by K and get the answer for it. Okay, get the answer for it. If ratio between them, if the ratio, okay, is something that is bigger than 10 to the power of 4 or 5, there is high chance that you can ignore x. You can ignore x. So if the ratio between initial concentration and K is 10,000 or higher, that means this reaction does not move, okay, to the right side. Not much, okay, not much. Mainly you have unreacted HX, and you're not going to generate much from, does not move, I should say here, much to the right side. You will have mainly unreacted. So whatever you are losing, you can ignore it versus initial concentration. Okay. So in this case, I can ignore it. The assumption is yes. How about this? What if the initial concentration was, let's say, 2 multiplied 10 to the power of minus 3? Okay, or let's say minus 4. Make it minus 4. Minus 4 divided by K, which is 7 multiplied 10 to the power of minus 6. That's going to be around, 200 times, or maybe maximum 1,000. In this case, I will say you can't ignore X. This is not going to be correct, but that one, it will be correct. Okay, you see the ratio here. Ratio is something here. So 2 to the power of minus 4. 2 to the power of 2 multiplied 10 to the power of minus 4 divided by 7 multiplied 10 to the power of minus 6. And that's going to be 28 actually, not 200. Sorry, 28. So you see, ratio is not, like ratio is a small number. That means you're going to lose plenty things. So if you have 2 multiplied 10 to the power of minus 4 and you subtract x from it, x is going to be significant. Okay, x is going to be significant. Why x in this case is significant? We did not change K. Yes, we did not change K, but the initial concentration is really small. It's really small. Any tiny thing we lose from it, it will be significant. Okay, so you see, if initial concentration is a big number, you can ignore x versus this. If initial concentration is a small number, any tiny thing you lose from it still is significant. So you have to go through a quadratic equation. Okay, so keep this one in your mind. Compare initial concentration versus K. And if it's 10,000 or higher, you're safe to go with the assumption. Okay. Let's go through two common ion effect. It says if you add an acid to this solution, what will happen? Because it says you're adding acid like HX, it will generate H plus and X minus. So we are generating H plus. The common ion effect here, it will be, because we are adding H plus, the common ion, it will be H plus. Concentration of H goes up, the common ion effect will move the reaction to the left side. So the reaction moves to the left side. Okay, so the correct answer, it will be this. Okay, add this one. What's the effect of adding base? If you add base, okay, if you add base, it will react with the OH, with the H plus, and it will generate H2O. So concentration of H, it will go down if you add base to it. Okay, H, it will be react with the it will react with the OH. H will be used. Because H was used, we need to generate more from H. So this time the reaction, it will move to the right side. Okay, so this one, if you add base, reaction, it will move to the right side. If you add acid, reaction, it will move to the left. So this one is to the right and acid to the left. Okay. How about K? K in both cases stay constant because we did not change the temperature. Next one, okay, we are adding silver ion. Silver ion, it will react with chloride and it will use the chloride and it will generate silver chloride solid. So concentration of chloride is going down. Why? Because we are using it. We are reacting the chloride with silver. So continuously this one is going down. And because it's going down, we need to generate more to replace the missing chloride. Okay. So that means the reaction, it will move to the right side this time. Anything that uses product will make the reaction to move to the right side, and we will increase the solubility this time. Solubility of lead iodide goes up because the reaction is moving to the right side. So the correct answer, it will be this one. Okay. So I'm gonna pause for a couple of minutes and I will get back with K versus Q, which is the reaction quotient. Okay, so now I'm gonna switch to reaction quotient. Which is Q, is QC. We show it by QC. What's the Q? Q is exactly like K, the formula for it, like K. The only difference when it comes to K, we use equilibrium concentration, while for Q we use initial concentration. So for example, if you have this N2O4 gas is under equilibrium with 2 mole of NO and NO2, and this one is gas, Kc is going to be concentration of product under equilibrium condition to the second divided by concentration of the reactant under equilibrium condition. And we have one, here one. QC is going to be, you write exactly same formula, same thing. You say NO2 product here, but instead of writing equilibrium condition, you say initial, okay, initial concentration, whatever we added to that container or say beaker or flask, divide by N2O4, and again we say initial concentration. So the difference between K and Q, and K we use equilibrium concentration, for Q we use the initial concentration. Now if Q is bigger than K, okay, if Q is bigger than K, okay, when this one is gonna be solid or possible, compare K with Q for this specific reaction. We want Q to be bigger than K. If the numerator of Q, which is NO2 or the product, high, then Q is going to be a big number. Okay, so if we have more from product, then like the Q is going to be a big number. So I will say in this case we will have too much, okay, too much from the product. We have too much from product, and our product in this case is NO2. So what do we need to do? Hold the reaction. It will go to the left side to crash some of them. Okay, to crash or to, like eliminate. And in this case, we don't have solid, so I don't have the right to say crash. And it will go back to the reactant to increase concentration of the reactant and decrease concentration of the product. If Q is smaller than K, in that case, we have mainly reactant. Okay, we have mainly reactant. We have too much from reactant. Okay, like in this case, it will be N2O4. So what do we need to do? That means still we can generate more from product. Okay, we can generate more from product until we reach the equilibrium condition. So the reaction, it will go to the right side. Okay, so the reaction, it will go to the right side to generate more from NO2 or the product. And if Q is equal to K, in that case, we are dealing with equilibrium concentration, okay? Or we are under equilibrium condition. So you can say the system is under equilibrium condition. Okay. So we have just enough from ion, whatever we added, from the reactant in the product to reach the equilibrium condition. So whatever we added, by chance, they're exactly equal to equilibrium concentrations. Okay, here the way I'm going to use this. So let's say they gave you such a question. Okay, they gave you K and you have some solutions, and they are saying predict whether we're gonna get solid or not. So you need to compare KSP in this case versus QC. Okay, KSP is given. Define the KSP is gonna be equal KSP of aluminum hydroxide is gonna be aluminum multiply concentration of hydroxide to the third. Okay, so QC is going to be concentration of aluminum at the beginning, initial concentration, multiply concentration of hydroxide at the beginning. So now get the QC. QC is equal to, what's the concentration of aluminum? Look to source of aluminum. We added aluminum as aluminum nitrate, and the concentration for it is 3 multiplied 10 to the power of minus 7. And for hydroxide, we added as a KOH, and it's 9 multiplied 10 to the power of minus 4, and it's generating only 1 OH. So I'm gonna use this number exactly to the third. But by chance, if this one was, for example, 3, then I had to multiply 9 by 3, and then I say to the third. Okay. So we have 9 multiply 10 to the power of minus 4 multiply 3 to the power of. Answer is 2.12. Or sorry, 19 actually. 19 multiply 10 to the power of minus 16. Okay, now compare KSP with the QC. QC smaller than KSP. That means we can dissolve more, okay? Still we can dissolve more, and so in this case, because KSP is a smaller, the QC is smaller than the KSP, I'm gonna say we're not gonna get, precipitation. We can dissolve more. Okay, we can dissolve more. Okay. So the reaction is gonna move to the right side. Reaction, it will move to the right side. Remember, when I say reaction, it is going to move to the right side. I'm talking about this one. Aluminum hydroxide solid is under equilibrium with aluminum plus 3 hydroxide. Okay. So the reaction is going to go to the right side. We're not going to get solid. Okay, we need more iron inside the solution. We did not reach the equilibrium concentration, so we have to keep dissolving. If QC was smaller than KSP, bigger than KSP, then the reaction, it will go to the back side and we will see precipitation. So in this case, we're not going to see precipitation. Okay, but that's the way, we use KSP. We compare KSP with the the QC, my bad. We compare QC with K. If QC is bigger than K, so we have too much from product or we have too much from the ions. So the reaction is going to go to the left side to generate the reactant. If Q is smaller than K, like the example I just did, that means I have too much from the reactant. The reactant has to go to the product side. And this example, we said we need to generate more. We need to generate more from this ion. So it will go to the right side and we're not going to have solid. How about Q equal to K? That one is going to be equilibrium condition. Okay, check this. If Q is equal to 6.5 multiplied 10 to the power of minus 5 and K is equal to 8.5 multiplied 10 to the power of minus 7. Okay, then you get Q bigger than K. That means we have too much from product or ions. Product or ions. So what will happen in this case? Reaction has to go to the left side. Okay, the reaction, it will go to the left side, so the reaction, it will go to the reactant side. And so we will see precipitation. So if you have, let's say, AX solid, and it says A plus X minus, this one, it says, here KSP for it, it will be A multiply X versus Q, which is initial concentration, multiply X, again, initial concentration. This one, it says Q is bigger than K. That means initial concentration of A is higher than equilibrium concentration of A. And the same thing for X. So we have too much from X and A. What we need to do, we need to drop them. So the reaction, it will go back and it will generate solid for us, or it will generate reactant. So we will see precipitation. Okay, last thing that I'm gonna do, say we can use delta G. Say delta G is equal to delta H minus T delta S. Okay, if T is 25 degrees Celsius and pressure is 1 atmosphere, and we're talking about 1 mole, and if you have concentration, it also is 1 mole per liter. In that case, you can say delta G under standard condition is going to be equal to delta H under standard condition minus T delta S under standard condition. If you use this one, the delta G that you get, we say, is a standard delta G. Delta G, okay? Because I use standard condition. If you're not using standard condition, then just put the temperature, put the delta S and delta H, and you will get the delta G, okay? For non-standard condition, I can use also this formula. Delta G is equal to standard delta G plus minus a correction. Okay, plus minus a correction. So delta G, it will be standard equal to standard delta G by applying a correction for it. Because when you deviate from the standard condition, something will go wrong. Pressure maybe goes up or volume goes down, something happen or something will happen, and you need to apply that correction. And the correction is going to be this: delta G is equal to standard delta G plus, okay, plus RT ln of Q. Ln of Q, it can be positive or negative, okay? So ln of Q, it can be positive or negative. So that's the reason I said plus minus X. Okay, next. If K is equal to Q, if K is equal to Q, that means you're dealing with the standard condition. Okay, sorry, equilibrium condition. If K is equal to Q, you're dealing with the equilibrium condition. Under equilibrium condition, delta G is equal to 0. Under equilibrium condition, delta G is equal to 0. Change with the Gibbs free energy is equal to 0. Why? Okay, A, B, let's say AB under equilibrium with C, let's say, okay? And we have a forward reaction, 1, and we have a reverse reaction. So we start with AB. Let's say here we got C. So this is going to be here. This is going to be delta G of reactant. And that one is going to be delta G of a product. Or C. Because this is equilibrium, you can have also a reverse reaction. You can have C, okay, it goes through this barrier, okay, and then it will generate AB. This is going to be delta G of the reactant, and that one is going to be delta G of the product. Look at the gap that we have. This is the gap between them. The gap here is positive. Delta G of the reaction is going to be delta G of the product minus delta G of the reactant. This is going to be a positive. Delta G for the reaction is a positive number. And in this case, if you subtract them, delta G of the reaction, delta G of the product minus delta G of the reactant. Look to this one. Delta G of the reactant, or C in this case for the second reaction, C to AB, second reaction, it will be a negative number. This is going to be a negative number. It's negative and equal to the first one. Okay, so let's call this one 1 and call this one second reaction. So delta G of the first reaction is equal to delta G of the second reaction. The only difference between them is the sign. One is positive and one is negative. Okay? So if they are equal with opposite sign, when you add them, they will cancel each other. So when you add delta G of reaction 1 plus delta G reaction 2, they are equal. This is positive, that one is negative. Your final answer will be 0. Okay? So that was the reason that I said delta G is equal to delta G0 plus RT ln of Q. And if Q is equal to K, or equilibrium condition, delta G, it will be equal to 0. So now we got 0 equal to delta G0 plus RT ln of, instead of Q, I'm going to write K. So the answer is going to be delta G0 equal to minus RT ln of K. If we know the standard delta G, we can get the equilibrium constant. R, you go with this number, 8.314 joule over mole to Kelvin, and T, temperature in Kelvin unit. So it's going to be temp in Kelvin unit. How about delta G? Delta G is going to be in joule per mole. If R is joule over mole, then this one, delta G, it has to be in joule over mole. So then you can cancel joule by joule, mole by mole. Okay, let's do one example about this one. Okay, we have an equilibrium. We are given delta G0 of the reaction. The temperature is given, so we can calculate K of this reaction. So we say delta G0 is equal to minus RT ln of K. We're looking for K. Ln of K is going to be equal to minus delta G0 over RT. Okay. I said delta G must be in joule, not kilojoule. So delta G0 is going to be minus 90.5. Multiply this one by 1,000 to make it joule. And then it says it will be joule over mole. So I get ln of K equal to minus 90.5. It has 90 and there is 90 from the formula, so it will be negative from the formula, negative from the delta G, so it will be negative to negative, it will be positive. This is 90.5 multiplied 1,000 joule over mole. Okay. Divide by R, 8.314 joule over mole to Kelvin, multiply temperature in Kelvin, which is 298 Kelvin. You cross joule by joule, mole by mole, Kelvin by Kelvin. You will not have any unit, and we know K does not have any unit. So we are on the right track. Okay, so ln of K is going to be equal to 90.5 multiply 1,000 divided by 8.314 divided by 298. That's going to give me 36.5. 36.5. So now K, base for line is E, so it will be E to the power of 36.5. And that's going to be 7.31 7.31 multiplied 10 to the power of 35. 15, my bad, 15. Okay, 15. So K is equal to e to the power of 36.5, which is equal to 7.31 multiply 10 to the power of plus 15. Okay. So K is really a big number. That means SO3, if you mix it with H2O, this reaction is almost one way, and you're not gonna get much, from the reactant, and mainly you will have product. Okay, look to the arrows. I showed one of them bigger than the second. That means the forward reaction is favored and the reverse not much. Why? Because K is way bigger than 1. Okay, so that's the meaning of big K. Okay, so I'm done with the chapter. I hope this lecture was useful, guys, and wish you really all the best when it comes to final exam. I hope you will do good with the final exam. Wish you all the best again. Take care.